So today's about randomized greedy algorithm for this general problem called submodular maximization. This is not something I've taught in randomized before, so I'll be happy to hear if you liked it or not uh, afterwards. But this is something people have asked me to teach several times. But the setup, the basic problem we're interested in uh, is pretty simple. So maximum coverage. This is slightly different than set cover, which we did previously. So you have some sets, you have some points, you want to cover points with sets, okay? But this time I give you a cardinality constraint. I say you can only take 10 sets. And you want to figure out the best 10 sets you can take. Okay, so 10 you can brute force, but if it's general K, then it starts getting a little harder. Okay, so that's the goal. You just want to choose sets that maximizes the size of the union. Of course, I can make this a little more interesting by putting weights on the points, and then it's going to be weighted point sets, but it's not a big deal. Okay, so that's the one basic motivating problem. Uh, right, so we've seen set cover before. We're trying to minimize the number of sets you need to cover all the points. We did LP rounding for this. Uh, and here you're trying to maximize the number of points while using at most K sets. So this is a packing problem before it was sort of a covering problem. I guess literally covering problem. Um, So I want to point out that if set cover is NP hard, the maximum coverage must be NP hard. Why? How? Just do? How do you do? Okay, so I gave you a black box that does max coverage. It takes sets, it takes K. How do you solve set cover? Yeah, you can just keep looking for guessing K. Yeah, and just go do. Yeah. Um, that's right. Turing complete Pac-Man. Okay, so we're going to study a greedy algorithm. Uh, oh, this is not a set covering. So repeatedly selects the set covering the most new points. Okay. Um, and then our question, it's a very natural algorithm. Our question is how good is the greedy algorithm? So, okay, let's say that K is 4, and I'll let you stare at this and try to figure, or maybe 5. Let's do K is 5 sets. So each red. So how many points? Is 5 too much? 4? You can cover 17? Is there really closely a 3D image comes out? You remember those? Or do those exist anymore? 5. Is 5 too much? Okay. I don't know. Okay, so let's just at least retrace what the greedy algorithm would do then, up to some ambiguity in what is a set. So which single set contains the most points? So I think it's this one. Oh, what did I do? Okay, that's one. Now, what's the next set that the greedy algorithm would take? So you're only looking at how many more points it's going to cover. So There isn't a billion fours. Okay. There's a four. Um, yeah, they're not necessarily disjoint. It's just going to try to grab as many more points as it can. So the second round, it got four more points. That's the score it considered. Um, and it will tend to be somewhat disjoint in the sense that you don't get double points for covering the same thing twice. But yeah, so the greedy algorithm will keep just trying to grab as many points in each step as possible. Uh, it's not necessarily optimal, but this might be something like what it does. All right, so okay, so how good is this algorithm? So we're going to study this in a slightly more abstract framework, okay, where I want to think about just being given some function f of s, and I'm going to try to take a set s to maximize f of s. Okay, and then we're going to leverage a few properties. Property one is that it's normalized. F of the empty set is 0, right? So if I'm not taking any sets, I'm not covering any points. Number two is it's non-negative. So f of s is always at least 0. Three, it's monotone. So as I take more sets, I'm only covering more points. It doesn't go down. Okay. Second half of the lecture, we'll figure out what happens when you lose this. And then the fourth property, the buzzword of the day, is that it's submodular. Okay. So, so if you have any two sets, right, and this is sort of like the Venn diagram, like A union B plus A and B. So at some level, having A and B is sort of more spread out or less extreme than like the union and the intersection. If that makes sense. It's more balanced. And it says, okay, the balanced one is better than the two extreme ones. Okay. Now this definition is a little bit less intuitive than the more intuitive one is decreasing marginal returns. So you can show that these two are equivalent, and this one's maybe easier to interpret. Okay, so imagine I have a set S, and I add an element E. I just write plus E means I'm adding one element to it, sort of abusing notation. I say, okay, how much did my value go up? F of S plus E minus F of S. Which sometimes we'll write this like E given S because this comes up a lot in the analysis. So this is like the marginal value. How much did my value go up relative to already having S? And it says that if S is smaller than T, S is a subset of T, the marginal value added to S is always at least the marginal value added to T. Okay, so like in economics, they'll have like utility functions. You have like a bunch of stuff, and it's like how much happiness, how much utility you get out of it. And there's this premise of decreasing marginal returns, which is sort of like the more stuff you have, kind of the less incremental gain from the next element, right? So this is the taco curve. So this is your utility on the y-axis, right? And then as you have more tacos, you get happier and happier, right? Until you're like kind of getting tired of tacos, and your happiness starts to go down, right? So if it's a one-dimensional thing, it'll look concave. This is sort of like a discrete notion of concavity. Okay? Yeah. Yeah. So f is a valuation function. So that's right. So it's not a linear function. It's not a modular function. So we're going to be looking at some objective function as sort of a black box, only subject to these properties, which turn out to capture a lot of applications, including coverage. So so all we're promised about this black box is that when it adds an element E, we're never promised anything. We're never promised it's going to be equal or anything. But we're promised that this marginal value will be decreasing in sort of your base collection S. The intuition is that, this often comes up again like in economics where S is the items you already have. it's all the things you already own, and you buy like another iPhone. If you already had an iPhone, it won't be worth as much or something, right? So whereas your first iPhone is going to be awesome, right? If you have up to 3 tacos, you're doing great. Fourth or fifth taco, you're like, I don't like tacos anymore. You get less happy. Yeah. So this is just an assumption. And it's all we're going to assume about the black box. And if we can understand, if the greedy algorithm performs really well for this general F, that's actually very practical, right? So there's a lot of like, I don't know, search engine results, right? Each additional result brings in more information, right? And you can measure information various ways, entropy or whatever else, right? And but of course, they're kind of overlapping, right? So the first new article is going to give you tons of information. The second article is going to give you some information, but you might have known some of it already from the first article. The third article, so on and so forth, right? So it's sort of like coverage, but in terms of bits of information, right? So you see this kind of framework come up in data mining a lot, machine learning kind of a lot, right? Here's something very practical. You can stare at a lot of things and be like, oh, that probably has decreasing marginal returns. Oh, that's probably monotone. So maybe I can apply a greedy algorithm to it, or some other algorithm appropriate for this kind of F. So in this case, we want to be as abstract as possible to have the most applications. Yeah. Okay, just takes a little bit of effort. Um, yeah, no, it's not that easy. I mean, I have to do it on paper. I can't do it that quickly. But I've done it many times before. If you're lucky, I can give it to you for homework. Oh, there's a different problem. Anyway. Okay, so the basic example then would be coverage, okay? The one you can keep in mind, where the elements correspond to the sets. Which sets are you taking out? You can take out most K. And then F is going to take your sets. It's going to calculate the union and the number of points in it. Okay. And we can check, it's normalized, because if I don't take any sets, I don't cover any points. It's whatever, non-negative, of course. You're covering a non-negative number of points. It's monotone. If I add another set, I'm not going to lose points. And in it's submodular, here it's easier to verify decreasing marginal returns. That's how many more points do I cover from adding a set? Well, the more sets I already have, the more likely I am to cover some of those points. Okay, so good. You might be wondering, where's the random part? That'll come later. Okay, so as a setup, we're going to first just study the greedy algorithm. Okay, so there I've kind of written it in this set notation, where I'm subscripting things so that you kind of know which iteration they come from. So you're going to do k iterations. Each iterations, you find the element that has the best marginal increase compared to what you already have. Right, so that E sub I given Si minus 1, that expands out to Si minus 1 plus, yeah. And then you repeat and you return it. Okay, good. So, first thing we gotta do is this lemma. Okay, so maybe as a little bit of extra notation to help you out, let's say that S star is optimal. So S star has at most K, has K elements. And what else is there to say? F of S star is equal to opt. Okay. All right. So if we wanted to prove this thing, I guess I have more space here. Oh, I can bring my notation with me. No, I can't. Okay. Okay, so let's say this is the optimal set, S star. Okay. All right. So I'll start like this. Right? So I'm trying to show that at some level, the amount of utility I'm getting, the right-hand side I can interpret as like, what's the difference between me and opt? Right? Going into that iteration, what's my room for improvement? And I'm going to get a 1 over k fraction in the ith iteration. That's the claim. All right, so I start with f of ei given si minus 1. How can I start relating this thing to s star? Oh, okay, so that would be true if s star contained si minus 1, but they might be just like disjoint and stuff like this. Yeah, so just because s star might have more elements doesn't mean you can apply that. Yeah. Well, what do I know about ei? Ei is sort of defined by one thing. Sorry. Is the maximum utility of any element, right? That means if I'm like looking at the optimum solution, any of those elements could have only helped me less than this element. So it's at least, if I sum over all the edges in T, sorry, S star, is T better? Whatever. F of E given Si minus 1. Okay, so that we know. Because there's K elements in the optimum set, and each of those individually I win. So now it's saying I'm winning over their average. Yeah. Okay, good. So somehow like I'm at least able to compare to each individual element in the optimal set. Okay. But eventually I want to kind of combine things. Uh, sure. Yeah, I don't mind expanding. Uh, if that helps. That's not going to get us everything. Okay, what if I did this to help out a little bit? Suppose I wrote, here, let me make this notation a little bit more helpful. I'm going to make this D and D, just to remind us. And then suppose I wrote, yeah, suppose I numbered S star as like D1 through DK, okay? And, uh, and I wrote this as D is equal to 1 to K, sorry, J is equal to 1, DJ. I'm not sure if that directly helps. Um, yeah. Yeah. There's two in the set formulation. Let me scroll back up. Yeah, this is always confusing. So in the set formulation, we are choosing sets, okay? And in the f of s formulation, you say you're choosing elements. So the sets from the application are the elements of this problem, of the abstract. There's an unfortunate doubling of terminology. So I am trying to choose a set of elements in this version of the problem. Each element corresponds to a set in the coverage problem. So in maximum coverage, I'm trying to choose a set of sets, right? A family of K sets. So that corresponds to a set of K elements. So one of those sets becomes elements, but the other one stays sets. Yeah. We try to make it as confusing as possible, to build a moat, around, yeah. Okay. But yeah. Okay. So, yeah. Hmm? Okay. But why? Okay. So I can write this. Why? Uh, so there's no monotonicity. So think in a bad case, S star is completely disjoint from Si minus one. So Si minus one of these terms only has. Oh, would it? Huh? So let's just be precise, right? It's not because of just because of monotonicity. Okay, so there's a couple different ways to do it, but here's one. So let me say that S star J will be the first J elements for any J. Okay? And so I can directly use some modularity here, where for each of these terms, Si minus 1 union dj minus 1. Oh, sorry, S star. I feel like S star was a bad choice. Okay. So all I'm doing is increasing the set it's relative to, so that only decreases the value. So that just directly uses some modularity. Now what? Yeah. Yeah, so now if you expand this, this will be a telescoping series. So this is really Sj star union Si minus 1 minus f of Sj minus 1 star union S of I minus 1. Okay. So at the end, you're left with f of S star union S of I minus 1 minus f of S of I minus 1. Okay. And then what's the last step? Or why? So the last step will be the answer, but the question is why? Monotonicity. Okay. Okay. So that's the proof. So yeah. Okay. So now it's just about taking this and translating it into an overall bound, right? So sorry for those taking notes. Um, okay. So now I want to bound something like this, right? So okay. Let me just make sure I do this. Okay, so what did we kind of show in our proof? We showed that f of if I expand it out, sort of my improvement in the ith iteration is at least 1 over k times the room I had for improvement. Okay. And if I rearrange this, right, I can write op minus f of s minus 1 is at most, this is a bit of an annoying rearrangement, opt minus f of si minus 1, right? So these are like gaps, right? So there's a gap in it, that's s of I. So these are like how far away I am from opt, right? This is gap after I iterations, gap after I minus 1 iterations. So it's going down by 1 minus 1 over k each time, right? So for example, f of s1 is at most 1 minus 1 over k opt, and f of s2 is at most, oh, I got it wrong. Sorry. Let's do this correctly and slowly. All right. Opt minus f of s0, of course, is opt. Opt minus f of s1 is at most 1 minus 1 over k opt. Opt minus f of s2 is at most, keep going, opt minus f of sk is at most, so that gives us that f of sk is at least 1 minus 1 over e opt. That's like 0.68 or something like this. Okay? Okay, good. So that was the preliminary part of the lecture. Because obviously we haven't done any randomization yet. Okay? But this is a classical thing. Okay, good. All right. Now our real challenge is trying to deal with f that's not monotone, but still submodular. So an example is like directed graph cuts. So you take, you're choosing vertices and you count the number of edges leaving the cut, or leaving S, directed out of S. So that's submodular, but it's not monotone because if I add a vertex, it might eat up some of these edges that are leaving. Yeah. No, sorry. So in that version, S is vertices. The elements are vertices, and f of s is going to count the number of edges that are leaving your set. So if I have an edge that's leaving and I add like this vertex, the opposite endpoint, it's going to swallow up this edge. Yeah. Or another way to put it, if you're trying to do a maximum cut, if it was monotone, you just take all the vertices, but that's not true. Yeah. Okay. So greedy doesn't work, but where did it go wrong? Do you remember? Where do we actually use monotonicity? It was sort of like in the last step of that lemma. So I think it's written. Yeah, so right after this sort of telescoping series, we applied monotonicity in the last step, right? Just to argue that S star union, our solution is at least opt, okay? But if I take that away from you, now you're screwed, right? So this is the basic technical challenge. Okay, so good. Oh, sorry. Good from a teaching perspective. Like, good midterm, good lesson. I don't know. Yeah, okay. All right. So this is going to be the main lemma we're going to use, and this is why I thought it would be interesting for a randomized class. So this is really has to do with submodularity. Okay. So here's the claim. It's about f of r, where r is a random set, and f is submodular and normalized, non-negative, non-negative. It doesn't have to be normalized. Okay. The claim is that if you give me a random set, but you promise that every element appears in that set with some bounded probability p, then your output is going to be at least 1 minus p times f of the empty set. It doesn't require f to be normalized, and I'll give you an application in just a moment. Okay, so f of empty set might be non-zero. So let me give this seems like, okay, what's the point of this? Okay, so suppose in our greedy algorithm, we somehow adjusted the greedy algorithm so it's somehow taking a weird random set, right? Maybe it finds an element and only adds it with a small probability or something. I don't know. And suppose for simplicity, I can guarantee that every element occurs in my random set was probably at most 1/2. Then I claim the expected value, this was the term we couldn't deal with, is that it's at least 1/2 of f of s star. Okay. But how do I apply this to get this? Because clearly s star is not empty set, right? Union inside and outside. That sounds dangerous. Uh, not sure. Uh, in any sense of the word, sure. um, yeah. No. So this would be a useful statement, right? This would be a useful statement if I can have this. And I'm claiming that this useless statement can be used to prove this useful statement. This does not require f to be normalized. It requires f to be submodular. Well, let me do something similar. Let me define g of s is equal to g of or is equal to f of s union s star. Okay. G is submodular. G has nice properties, and I can apply the function to G. So the empty set is going to give me the value of S star. Okay. And then you can imagine if I could plug this back into our analysis, something will get weaker, but something will come out of it. So it does require non-negative. So we should probably do, uh, yeah, and non-negative. Uh, yeah, it'll require non-negative, but not normalized. It requires submodular, but not monotone. The lemma or the algorithm? So that theorem is just before to remind us what we already did for monotone. Okay. Okay. Yeah. Is what? No. No. For any random set R. So in the worst case, you get this bound. Yeah, I don't require any independence across E's. Yeah. No, it's not just an annoying amount of summation notation. Maybe it is. I don't know. Um, okay. All right. So let's look at this. Okay. What are we looking at? All right. So to prove this lemma, actually, you do this kind of funny thing where you take a continuous perspective. Okay. So given a set function f, right? I kind of think of that set function over n elements as like values on the corners of the hypercube in n dimensions, right? Those 0, 1 bit strings corresponding to sets. And so continuous extension is any like continuous extension to the rest of the hypercube, right? So it's any function f over the whole hypercube that agrees on those vectors representing sets, right? So any examples? Anyone want to suggest an example or idea of one? So what would linear programming? So okay. So you have some function of the form f of x, right? Where x is a vector of values. So x is assigning a value between 0, 1 for every element. Hmm? That will just give you some. Well, you want to do some function related to little f. Yeah. Yeah. So I can do something like, oh, what's the expected value of f of r, where r is an independent sample, and the probability of e and r is equal to whatever is the value in the vector. Okay. So that means if you give me one of the corners, some incidence vector of a set, then that's a deterministic set that always has those elements. So you'll get the value you're looking for. So in general, you can take your vector x and come up with any distribution of sets R where the marginal values agree with x, and you'll get some continuous extension. Okay. So what we're going to do is we're going to analyze what is the worst from what's the random set that gives me the worst value. Okay, so I have a typo, not surprising. Okay, so that's sometimes called the convex closure. Okay, so it's saying, okay, you're taking as input some probability vector over your elements. What is the worst set? So it's the infimum over all possible random sets R. So you get the constructive distribution and you get the expected value. And your only obligation is that your margins must match. Okay, so it's a question of what is the worst distribution for a submodular function to minimize the value? What is the smallest one? Well, you can try to guess. No, you're not supposed to know this. You're not supposed to know anything. So remember, in a submodular function, right, you have decreasing marginal returns, which sort of says that like overlap, if you're trying to maximize, and overlaps are bad, right? It's like coverage, you get discounted when things are, co-occur, right? I don't think so, but well, maybe. Yeah, actually, yeah, I think yeah, right? So intuitively, decreasing marginal returns or the initial definition of A plus B, it's saying, okay, when you take combined things, values go down. Yeah, so so correlation would kind of decrease value, right? When things occur together. So I give you some vector saying, okay, this point have to be in 10% of the time, this point is 20% of the time, 30% of the time, whatever, right? What's the most like correlated random set I can come up with that'll match the margins? Yeah. Yeah, in fact, this looks a lot like something we've done before. It's basically a line sweep. So this was observed by Lavatz. So all these values are between 0 and 1, right? So let me choose a random value between 0 and 1 and take all the elements with value greater than that threshold. So that's like super correlated rounding. In fact, maybe it's not a coincidence that cuts are submodular. So we're going to look at correlated rounding, and then we want to argue that this is best possible, I mean, the minimum one. Okay? So this is going to use submodularity. Yeah. Okay, so um, okay, so we want to prove this. Okay. Any ideas? So let me maybe as a hint. So this Lovat's extension, this correlated rounding, you can also think of it as like, okay, we'll say that a random set has like a chain support if all the sets it can realize form some kind of increasing chain. So this is an increasing, some chain, right? Because the STs are only decreasing as T gets bigger. Yeah. All possible choices of distributions are, of sets, random sets are. So it actually will be a min because it's a compact space, so it will be realized, right? But no one's keeping score. So, but you get to choose any random set you want, but you just have to make sure your margins match the given vector. And so the claim is that the worst, the smallest possible distribution, a minimizing distribution, is this super correlated sweep cut. No, R is a distribution, is a random set. So I give you P, and then you give me R, which is a random set. So you construct a random set, and I evaluate the expected value of your function. But the rules are you have to make sure that each element occurs with the probability given by the vector. So what's the random set R with those margins that minimizes the expected value? The left part of the curly brackets is the value. The right part is your constraints. You get to choose the random set R. So you define a distribution, and the question is, what's the worst distribution? Uh, Such that probability E and R is equal to PE? Sorry, which question? It's a vector that gives values for every element, which they're between 0 and 1, so you can interpret them as probability values. Oh, okay. Well, we can continue next time. Um, so this is the question then. If F is submodular, then why would this correlated rounding you can think of, right? You can also think of this as rounding. You need to produce a random set R where the margins match the values. Why is this sort of the rounding scheme that minimizes the expected value? Okay, so that's where we'll start next time. Uh, yeah, sounds good. All right, then I'll see you guys Wednesday. All right, let me remind us what we're doing last time, get us caught up as the last few people trickle in. So we're discussing greedy algorithms for maximum coverage and generalizations. So so maximum coverage, you're trying to take a limited number of sets and cover as many points as possible. But more generally, you're doing some kind of set function maximization. So you have this black box f of s. You're allowed to just give it a set s or return a number. And you want to maximize it subject to taking out most k elements in S. And in this game, you're promised these properties, right? So some are kind of very natural, like the empty set has value 0. All the values are non-negative. Monotonicity, so if you put in a bigger set, you could get back a bigger number. And then the interesting one in this lecture is submodularity, which is just anything satisfying this inequality for all A, B. So give any set A, B, the value of the two of them separate is sort of like at least the value of the Venn diagram parts. So a more natural, or it's equivalent to this, which is maybe easier to interpret. So so here's some set S, and here's an element E that I'm adding to my S. So I just use plus to mean I'm adding an element to a set S. And so this difference is, okay, I have a bunch of stuff S and I add a new element E. How much happier did I get? How much more did the F value go up? It's called the marginal value. And this says that for the same element E, if you have more elements already, your marginal value will be smaller. Okay, so this is sometimes called decreasing marginal returns, right? It's like a basic premise in like economics or something, right? We're risk adverse because of decreasing marginal returns. And again, the example I gave was like, you like tacos. As you eat tacos, you're getting happier and happier and happier. But each successive taco is like less exciting because now you've had like 6 tacos. And at some point you want to throw up, and now you're actually getting unhappy with more tacos. Okay, but so this is just like a thing. So we can apply that to coverage. So in coverage, it's a little confusing because of this set and set gets overloaded. In coverage, you're trying to take set to cover points, k sets. In the set function formulation, you have elements, and you're trying to take a set of elements to maximize f. Okay? So if I'm mapping these over, the sets in the coverage problem correspond to elements that I'm putting into f. And f of s will be f of a collection of sets, will be the total number of points I'm covering. Okay, it's easy to see. So decreasing marginal returns is like overlap. Oh, I've already taken some sets, so this next set, some of the points are already covered. It's not going to give me as big a gain when I take it in my collection. Okay. And what we spent a fair amount of time doing last time was discussing the greedy algorithm. Here it's put in the set notation. But this is very simple. So I just, I'm trying to take k elements to maximize f of s. And I just keep taking the element that gives me the biggest boost, biggest boost, biggest boost. Okay, so in coverage, I just keep taking the sets that covers the maximum number of new points. And we did this together. Maybe I'll annotate it a little bit. But we argued that this is how much value you're getting in the ith iteration. And that it's some 1 over k times a fraction of sort of like the room for improvement, op minus your current value. Okay, so I'll just like annotate it to refresh our memory. Okay, so this element I take, I know had the best marginal value among any element. So in particular, it's better than any of the elements in the optimal solution. So those di's are the elements in the optimal solution. So it's bigger than the average of them. Okay, and where we use some modularity is, okay, we've taken S star and we just indexed it D1 through DK, and I'm writing S star of J denote the first J of those elements. Okay, so I can take this second part, sort of the marginal value relative to what, and I can extend it with elements from the optimal set. Okay, that's only going to decrease the value because of decreasing marginal returns. So, oh, what's the marginal value of dj? If I increase the relative set that I'm adding to, that marginal value goes down. And that just gives you this telescoping series. Okay, so in the last line it says, okay, you're getting at least a value of f of s star union my set relative to my set. Okay, and then by monotonicity, this bigger set is at least the optimal set. Okay, so this is the key thing. Okay, so from there, now you just rearrange things and you just kind of do the thing, and then you're going to get that you get at least 1 minus 1 over e of opt. Okay. Now, so okay, so the part we're getting into was how do I maximize f when f is not monotone? So it's still submodular, it's still non-negative, it's still normalized, but it's not necessarily monotone. Okay? And we only use monotonicity in one part, which is the last line of that lemma, where now it said f of s star union si is at least f of s star. Okay, that's the only part I used it. But that's not necessarily true anymore, because you can take opt and add your elements. It might make the score worse. Okay, so an example of of such a function f that's not monotone is like graph cuts, right? So maybe I have a graph, and for s, the elements will correspond to vertices, and I'll count the number of edges that leave it. Okay, so you can show this is submodular, but it's not monotone. Maybe I have an edge from here to here. If I add this vertex, it kills off that edge that used to be going out of my cut. Right, so trying to maximize the outcut, subject to taking only k vertices or something. Okay, this is something that the greedy algorithm won't. Okay, so good. So to overcome this, I introduced this lemma. Okay, which is about what is the expected value of f of r when r is a random set. Okay, so lemma says, okay, so suppose r had the property that every element appears in R with probability at most p for some fixed value of p. Okay, then the expected value of f of R is at least 1 minus p times f of the empty set. Okay, only assuming f is submodular. Okay, you might think, oh, f of empty set is not very interesting. How's that going to help us? Well, okay, imagine we could adjust our greedy algorithm somehow. We'll figure out how by the end of class. And had this property where like, oh, somehow I'm taking sets randomly instead of deterministically. So I can guarantee that, let's say that every element appears in the set I have so far is probably at most 1/2. Okay, because you're doing something random or something. Maybe you drop some elements, who knows? Okay, then at least in the last step of that proof, I can argue that f of s star union si is at least 1/2 of f of s star by not looking at f, by looking at this function, g of s is equal to fs union s star, which is also submodular. So I can apply the lemma to this. The empty set will correspond to f of s star. Okay. And you can imagine, oh, if I plug this in, I might be able to roughly replicate some of the previous proof and get some kind of bound. Okay, maybe that's believable. Okay, but the question is, what is this lemma? How do we prove it? So there we actually start looking at continuous extensions of f. So f is originally a set function. It takes a set, outputs a value, right? And so by continuous function, I'm going to think about continuous over like the hypercube. So I can think of each so that means like, between 0 and 1 for every element. So the corners will correspond to the edges. Like 1, 1, 1 will be those elements are in my set and the rest are not. Things like this. Okay? So this capital F is an extension if it agrees, some function capital F is defined on the whole hypercube, that whole continuous space, but agrees on the corners with your original set function. And so one generic way, or one example that was suggested in class, in fact, it's an important one. It's called the multilinear extension. But for example, suppose so you're evaluating f of x, where x is a bunch of values between 0 and 1 for every element. So one way to construct such a function is to interpret these as probabilities for every element and say, okay, what about a random set R, which is an independent sample where each element gets sampled, with probability equal to its encoded value. Okay. And then I just return the expected value of this random set. Okay, how about this function? So this function will be an extension because if x was a 0, 1 vector, then the corresponding set R will be like deterministically the set elements with ones on them. And that's it. Right? So the expected value would just be f of that set. So in general, it doesn't even have to be an independent sample. If you find any random set R where each element's marginal value, the probability of the element being in R, is equal to the encoded value, that'll give you some continuous extension of little f. Okay, so we're going to take this continuous point of view. Now, of these, okay, you could ask, what is the minimum? Right, so any distribution, any random set R where the marginals match x will define some kind of continuous extension. And now you can ask, what's the continuous extension, or what's the random set R with the same margins that minimizes the expected value of f of R? This is called the convex closure. You can show this is convex as a function of x, but that's not too important here. Okay. But this is just a structural question. So if f is submodular, then, so I give you certain probabilities, right? And I say, okay, you have to make me a random set where an element appears with the probability given by that vector. And I say, okay, find me the random set that minimizes the expected value. I know we kind of did this last time. So either you can recall it or you completely forgot and you can solve it all over again. What would be such a set and why? Yeah. Yeah, and you remember why? Yeah, so intuitively, kind of decreasing marginal returns says that, it's like coverage, right? So overlap, you don't get credit for, right? So what you want to do is you want to come up with a random set where things are very correlated, right? So you want the margins to match, but you want the elements to appear at the same time because that's sort of like taking many sets that overlap, right? If you had, let's say you have two sets with some overlap. If you want to maximize the value, and let's say they both had marginal value of 1/2. If you want to maximize, I would make a random variable with probably 1/2 is just this set. It's probably 1/2 is just this set, so I never have to suffer the overlap. But if I want to minimize the value, I make a random set that's both of them with probability 1/2 and neither of them with probability 1/2. Right? Then I'm always paying the overlap. So that's the idea. So that can be expressed compactly. This was observed by Lovatz. And it's essentially just like the line cuts we did for max flow min cut. In fact, it's not a coincidence that cuts are submodular. And okay, so you're going to draw T between 0 and 1 uniformly random, and you'll include all the elements whose value is at least T. So if an element has value 0.3, there's a 0.3 chance of T being smaller than 0.3, so you'll take it 0.3 of the time, right? So you're gonna, yeah. So that's just like trying to stack them up and trying to force them together as much as possible. Okay. So, so that's the intuition. How do I formally prove it? Any ideas? Linear of expectation and do some submodularity. Yeah, I mean, I guess we are looking at the expected value of a submodular function. Yeah. Oh, well, maybe to clarify. So I'm trying to argue that this set really is the minimum one. The general distribution, a general R. Yeah, okay, so maybe one, okay. So another way to think of ST is that if you look at the support of ST, the sets that can arise, they form a chain, right? Because S of point 1 is a subset of S of point 2, which is a subset of S of point 3. As you go, the sets only increase in size, so it forms a chain, okay? And if you think about it, that's the only way to get a chain that satisfies the margins. Because if a chain, then if some element has probability bigger than another element, it needs to always be present when the other element is present and stuff. Okay. So another way to state this lemma is that the best set R must be a chain. Okay. Or there's always a best set R that is a chain, because the only possible chain is this function we defined. The support is a chain. So we can say one approach is like this. Suppose R is some random set that has the right margins, but it doesn't have a chain. I mean, the support is not a chain. Okay, so, but there exist two sets, A, B, that aren't subsets of each other. Okay, but both the probability of A, R is equal to A, and the probability that R is equal to B is greater than 0. Maybe without loss of generality, I'll say A1 is bigger than the B1, which is bigger than 0. Okay, so that's one. If I can take this and maybe like replace R with something without the crossing, right? And then I can keep doing this, that would be great. Yeah. Okay, yeah, so let's do that. Let's look at I'll call it okay, T will sort of like uh increase probably that T is equal to A union B, and so I'm going to take R for starter. I'm kind of being very loose here, and I'm going to increase it by, I'll call this delta. I'll increase this by delta compared to R, okay? And then, oh, I wrote increase and the up arrow. So, and then I'll decrease compared to R, probably that's equal to A, and the probably that's equal to B by delta. And in fact, B will be eliminated from the support. Okay. So, okay. So this will preserve the margins because it's sort of doing the Venn diagram thing, right? Like uh, elements in A and elements in B, they're going to go down a little bit from here, but they're going to go up by the same amount here. If they're in both A and B, then it's going to go up by 2 delta. So you'll get that back. If it's only in A or it's only on B, it's going to go down by delta and then it's going to go up by delta on the union side. Okay, so that T will also satisfy the margins. But we want to show that the value is small. I mean, the value doesn't go up, right? So how come that this will be good from a f of t point of view? Or, yeah, f of the... So we took A and B and we've kind of uncrossed it, right? I'm kind of replacing the probability mass with A union B and A and B. But I'm looking for like the smallest possible value. So I want to argue that uncrossing doesn't increase the value. Yeah, it's exactly the submodularity inequality. So we have that f of A plus f of B is at most, that's the wrong one, is at least f of A union B plus f of A and B. So when I replace the probability mass of the two on the left and increase the probability mass of the two on the right by equal amount, then the overall average is only going to go down. Okay, so submodularly will keep the value down. So I can, at some level, you can take R and just repeatedly uncross, and the value will never go up until you have no crossings left. If you want to formalize this a little bit, you can say, okay, give me the set R with minimum value that also minimizes the expected value of, say, the size of the set squared. You can also see that this will decrease the value by convexity, and there's some compactness that that value will always get minimized and it will be attained. Okay, but that's the basic idea. If you had a solution, some set R that was really good value, but it had crossing sets, you could uncross it without increasing the value. Eventually you get something that has no crossings. That means it's a chain. That means it must look like our line cut. That's this uncrossing. Okay, so good. All right, so now this one I think you guys can guess. All right, so we actually know something about the convex closure of a submodular function f. We even know like an explicit form for it. Okay. Now let's go back to our original lemma, which is the one we want to use in the algorithm. If I have some random set R, and I know that every element in R the margins are bounded by P, then I'm claiming, and F is non-negative, then I'm claiming the expected value of FR is at least 1 minus P F of the empty set. Yeah. Exactly. So let me do it a little bit more slowly. So suppose let's make some vector x, which gives you all the margins, right? So all I know is that x is at most p times 1. Yeah. So the expected value of f of r, well, it's at least the convex closure of x, right? Which is the expected value of f of st, where st is constructed relative to x, is the line cut. Okay. And so this is at least expected value of f of st given t is at least p, or maybe strictly bigger than p, doesn't matter, strictly bigger than p. times the probability that t is bigger than p. Okay. So what is this term? So first I dropped off some non-negative terms, so that's okay. So what's this term for our x? What's s of t when t is at least p? Okay, so maybe there's a little bit of confusion. So up here, this should be our x. Sorry? F of empty set. So there's no element with value at least t. So s at least p. So s of p is empty. So this is f of empty set. And then what's the probability that t is bigger than p? 1 minus p. Okay. So it's very slick. Yeah, so somehow this lemma is really a function of uncrossing, right? And that can actually let you make strong statements about like the worst possible R and things like this. Because otherwise the assumptions of R are like very minimal, right? Yeah. Yeah. So I did not actually even write the right thing. There should be F minus, which is corresponding to this F minus, the convex closure. I'm sorry? Yeah. So this is some set with margins R. So it's better than the minimum set with margins R. Yeah, sorry if that threw people off, because that's sort of the most important single bit that could have been on the proof. Yeah. Yeah. So we're promised that every element appears as probably at most p for some fixed p. And remember, S sub t is taking all the elements as value at least t. So if t is bigger than p, then this is nobody's left. Okay, cool. Good. We're making good progress. Now, oh, that's no fun. Okay. All right. Okay, so let me tee it up for you guys. So the greedy algorithm works great when f is monotone and submodular. When things are not monotone, there's this one step, very trivial one line, which you probably didn't think of much originally, that doesn't hold anymore. Okay? But as sort of a hack to, we won't get the same bound, but we could get some bound, right? If you can somehow make something like greedy, except guarantee that sort of any element you take, maybe you only take with limited probability, then you can use this inequality to get over the monotonicity part with some loss. Okay. So what are some ideas then? How can we try to hack or adjust the greedy algorithm? I guess it's going to become a randomized greedy algorithm that on one hand is sensible, and on the other hand can help limit the probability I take any element, right? So you don't want to deterministically take the best element, then you're screwed. So any ideas about how to? Okay, so yeah, let's just start with the first iteration. Maybe I'll only look at half of the elements and then take the best element, right? And then maybe you can argue that, okay, hopefully I'm taking at least half of the elements from up, then this element should be better than, okay. So maybe each iteration, I only look at half of the elements chosen randomly, right? And, yeah. Okay, so, fine, fine. Um, Now, that means that each chance there's at most a 1/2 probability that a particular element will get taken. So let's say some element has the best margin, right? And there's only 1/2 chance you'll take it because you only sample it. Next round, one half, at most one half chance. So after 10 rounds, is there an upper bound on the probability I take it? Huh? Oh, okay, just sample half of them right away. Oh, maybe that would work. Oh, well, it's at most K, so I guess you just get stuck and you terminate. Yeah. So one thing nice about submodular is that you can always like duplicate elements for free, or if you take multiple copies of the element, it just doesn't add anything. Ah, okay, because maybe only half of opt is left. So this is actually not it's not going to be our final algorithm, but I think this will work. Okay. So one idea is just sample was probability one half. So I took the original ground set and I subsampled just half of them randomly, right? So one question is, what is the expected value of the optimal elements that you keep? Okay. Well, okay, here's one way. By submodularity, I know that, let me write S star. Okay, this is not about it. So I know that if I look at the elements I sample from S star, and I look at the elements that I don't sample from S star, sorry. So this ground set N prime is supposed to be the subsampled set. Okay. So here's like, oh, let me split the value into two, right? The ones I sample, the ones I don't. And this is at least what? The union and the intersection. No, S star is the original opt, right? You want to make sure that there's enough value captured in N prime. Um, and so this is at least f of S star, which is their union, plus f of empty set, which is 0. Okay. So one of the two halves always has at least half the value. And by symmetry, you might have either half. So you actually expect to capture half of the value in your random set. And then meanwhile, any element you'll take was probably at most one half. Okay, so I think that might work. That might get you'll lose 1/4 overall because you'll lose a factor of 2 here, and then you'll lose another factor of 2. Okay. Okay, that's actually not a bad idea. We're going to do something a little more clever. But at least that builds some intuition, yeah. So even something as simple as just introducing some randomness in a very simple way by sampling half the elements at the beginning is already getting you something if I'm not mistaken. I could, of course, be mistaken because I haven't done all the way through, but okay. So here's maybe then a different algorithm that we'll look at. Okay. So, I mean, maybe it just starts with the first iteration, right? Rather than taking the very best element, let me find the k best elements. And then out of the k, let me just choose one of them uniformly at random. So that will sort of dampen the probability I take any element. I mean, any element can be taken as probably at most 1 over k. And there's only k rounds overall. So any element, there will be a constant chance we never take it, no matter how good it is. Okay. So that's the algorithm. Each time you're gonna try to find the best K, and then you'll just sample one of them uniformly at random. So you can see some elements of greedy, right? You're trying out the best case, so there's something aggressive about it, but then you're still injecting some randomization. All right, so I think here I just left it blank so that we can analyze this thing. And maybe because I was running out of time making slides or something. Okay, so let's try to analyze this algorithm. And maybe we'll start with how much progress do I make uh, in each round, right? So I'm really trying to bound something like, maybe we can even do fix, suppose you fix si minus 1, right? So you've already done I minus 1 rounds, and we'll just look at the ith round, right? So you have this random element ei, and here's the marginal gain you're getting in the ith round. Then you just pick a k of them, yeah. Any k. Uh, yeah. Yeah. I'm sure that typo is also there in the notes then. Okay. All right. So we can do a similar style analysis before where I want to figure out the marginal gain in the ith round. We'll get something weaker, but hopefully it'll still be useful. Okay. So what should I do here? We'll do conditional and si minus 1. So that's fixed. And yeah, then I don't have to write quite as many e's around everything. How can we do this? Ooh, how can we do this in 10 minutes? Yeah, this is starting like the other proof. Yeah. BR, yeah, a high level. Yeah. Yeah, it's going to look very similar, but we're just going to take it step by step together. Yeah. Yeah, that's a good first step. Right? Just because we're choosing one of these elements in R uniformly at random. Okay. So good. These are like the K best elements, right? Yeah, or no, there's no randomness left. In fact, there's actually no randomness left anymore, right? But it's better than any K elements. Yeah, for whatever R. But in this case, the algorithm does choose R to have K elements. Yeah, yeah, yeah. But which one would be most helpful for us? Well, okay, okay. So I want to take some step here. Eventually, I want to say I'm making some progress towards opt, right? So this is the part. This is the greedy part of it, right? These are the K best elements. Ah, good. So that's the best set of K elements if I'm not worried about submodularity, just like the unit marginal values, right? And so that's going to be at least the K elements in opt. Yes. Or maybe to be consistent with some of our notation from before, I'll write D. Okay. All right, this looks familiar, doesn't it? This is exactly where we got to before, with just deterministic greedy. Okay, so here we can do that submodularity where we extend SI minus 1 to telescoping series and things like that. So I won't rewrite that again. And you get 1 over k f of s star union s of I minus 1 minus f of s of I minus 1. Okay. So we've recovered we're the exact same thing from the deterministic. In fact, so we've lost nothing, right? That's great. So you can actually expand out the k choices and you're fine. Now, okay. Now this is the thing, right? This is the thing that we've been obsessed with the whole time. So now if I don't condition, if I remove the conditioning on s of I minus 1, right? Okay. So what is this? Okay, so we want to figure out the probability that any element could be an s of I minus 1, right? So this is my random set. This is an optimum set, right? And I want to apply my lemma to this set. So I want to argue that any element E can appear in this set with some limited probability. Yeah, yeah. So it won't get picked in the first round. It's probably at least 1 minus 1 over k. It won't get picked in the second round. It's probably at least 1 minus 1 over k. So so your P is at most 1 minus 1 over k to the I minus 1. Okay. And here, I'm not going to try to do the calculations on the spot because I know I'll screw up. This is at least, this looks like about e to the minus 1, but it's at least e to the minus 1 for any k. And you can carefully check this. Yeah, I won't call it AMGM or anything that you can call me out on. Okay, but this you could check. Okay? So this will give you at least, uh, oh, but it's 1 minus p. So you get 1 over e f of s star. Okay? So because it's I didn't print the lemma. I should have printed the lemma's right there. Because it's 1 minus p times f of empty set. So the 1 minus over e becomes 1 over e. So we put that all together, and now if I remove the conditional expectation, okay, we have at least 1 over k, 1 over e f of s star minus f of si minus 1. Oh, do I want to be more careful than this? Let me check. I might not want to do the 1 over e part just yet. Yeah, okay. We're going to want to be a little bit more careful actually. So if I don't drop in the 1 over e part yet, then you'll do 1 minus 1 over k to the I minus 1. Okay? We're going to hold on to the approximating until at the end. Okay. Good. So, oh, you should. Yeah. Okay. So, okay. So, I can rewrite this as the expected value of f of si is at least, let me call this q, 1 minus 1 over k, so I don't have to write it over and over again. Q to the I minus 1 over k opt plus q times the expected value of f of s I minus 1. Is that correct? Okay. Let me do it more slowly. Forget the q for a moment. Okay, so we have, so if I rearrange, right, because this is f of si minus f of si minus 1. So this is at least 1 over k times 1 minus 1 over k to the I minus 1 f of s star plus 1 minus 1 over k expected value of f of s I minus 1. Okay, so I've just rearranged, and it's getting notationally a little annoying. Okay, so what happens if I just like unroll this all the way through? So for S1, it's at least 1 over k times opt plus 0. Okay, so expected value of f of S1 is at least 1 over k, and I'll just write opt because that's f of s star. Right? Correct me when I make a mistake. As you know, I probably will. Okay. The expected value of f of s2 is at least, I'm going to use this q notation again. Q over k opt plus q over k opt, which is 2q over k, where q is 1 minus 1 over k. I didn't want to write it again and again. Okay. And then we look at the third one. Expected value of f of s3 is at least q squared over k plus 2q squared over k, which gives 3q squared over k. Okay, does anyone see the pattern? Okay. Expected value of f of sk is at least q to the k minus 1 over k. Well, maybe I can do it in terms of I. Si is at least q to the I minus 1 over k times opt plus I minus 1 over k q to the I minus 1 opt, which is I times q to the I minus 1 over k times opt. Okay. So once I becomes k, you'll get k over k, that cancels out. And then q to the k minus 1, that's 1 minus 1 over k to the k minus 1. That's your 1 over e. So somewhere on the margins, just in time, we get the expected value of sk is at least 1 over e opt. Okay. Okay, so that's it. I'll note that this is actually, we don't know the answer to this problem. So 1 over e was the best bound 10, 15 years ago. And then like a progressive sequence of more and more complicated algorithms, but sort of centered around that key lemma, the uncrossing lemma, has gotten to bound like, it was like 1 over e plus 0.0001 for a while. And then recently, and it's like about 0.38 or something. And then most recently, it got over like zero point 0.4, but it's still very messy. And it's clearly like not the right answer. It's such a basic problem. There should be like a clean bound somewhere. We should understand as clearly as we understand the monotone setting. That we know is tight. In fact, it's not even NP hardness. It's also information theoretically tight in the black box model. So that's, anyway, just a problem. Okay. All right, we'll end it there. So next time we'll do coding theory, which we're supposed to start today, but that's okay. All right, thank you.